All right, so let's do some easy physics. The figure shows a block of mass m, block 1, that is attached to an end of an ideal spring. So these guys are together. So nice. Force constant k, just natural, and natural length L. Okay, so this is at equilibrium. So nice. The block is pushed, so it's compressed to 3/4. All right. And released from rest. Just as a spring extended to its natural length, the block collides with another block, also mass m, at rest at the edge of a frictionless table. When block 1 and 2 collide, half of its kinetic energy is lost to heat. The other half of block 1's kinetic energy is divided between block 1 and block 2. Okay, since half is wasted, each block is going to get 1/4 kinetic energy each, right? Because half of half. The collision sends block 2 over the edge, where it falls a vertical distance h, landing at a horizontal distance r. So nice. Okay, so la-di-da. What is the acceleration of block 1 at the moment it's released from rest from its initial position? Write your answer in terms of blah, blah, blah. Okay, well, we're figuring out acceleration. It's going to come from the spring force. So force on the spring is going to equal negative kx. We're not going to really worry about the negative here. So the force is going to equal k times how much it's displaced. Well, how much is it displaced? Well, this is 3/4 L, so this is going to be 1/4 L. 1/4 L. So that's the force, but we want the acceleration. Maybe you've heard of this little guy, F equals ma, right? So we know that F, which is equal to KL over 4, I'm going to put it like that because it's going to have another part in a second, equals ma. So that means A is equal to KL over 4m. So beautiful. Okay, if V1 is the velocity of block 1 just before impact, show that the velocity of block 1 just after impact is that. Okay, so we'll use dark blue here. So what we have is we have 1/4 of the kinetic energy, right? That's what we wrote down as notes. Well, so that means that the post kinetic energy is going to equal 1/2 mv squared over 4. Nice, and this is V1. So your post KE is going to equal 1/2 mv squared is equal to 1/2 mv squared V1 squared. So we just got to solve for V. Probably making it harder, but oh well. Whoops, I forgot the over 4. Okay, so square root, right? So V is going to equal the square root of V1 is going to be V1 squared is V1, the square root of 4 is 2. Ta-da! And that's what they wanted right there. Let's do the next one. So we'll go purple, I guess. Determine the amplitude of oscillations of block 1 and block 2 of block 1 after block 2 has left the table. Write your answer in terms of L only. Okay, so here's what we have. We know what the speed is. We know it has 1/4 of the speed, 1/4 of the kinetic energy, right? But what we're interested in is, since it has 1/4 of the kinetic energy of before, right, from there, we know it has 1/4 of whatever the spring energy was. So we know that the spring energy post is going to equal the spring energy pre divided by 4. Because the spring energy is equal to the kinetic energy at the collision, because it's at neutral, at equilibrium. So that's what we're going to figure out. We're going to figure out what the displacement is for here, because at both situations, there's no kinetic energy, so it's going to be easier. So spring energy post is going to be 1/2 K x squared. This is what we're going to be solving for right there. And that's going to equal your spring energy pre over 4, which is 1/2 k times x. How much was this displaced? Originally, it was displaced by that 1/4 L. 1/4 L. And that's squared, and we're going to divide by 4 because it's a quarter of the energy. Nice. Let's get rid of some stuff here. We can cancel out the 1/2, cancel out the x, cancel out the squareds. How about not? All right, let's squeeze this all together. So x is equal to, so we got 1/4, which is 1/16 after you square it, times 4, which is 1/64th. And then L squared, and then square root. Now, so what it's going to turn into is x is equal to 1/8L. I guess you could have square rooted it first and it would have been a lot easier. Oh well, YOLO, right? So looking at the next one, we'll use green. Determine the period of oscillation of block 1 after the collision. Writing your answer in terms of TO, the period of oscillation that would have if it did not collide. Period, well, the period's going to stay the same. So TO. Why does it stay the same? It stays the same because your formula is T is equal to 2 pi square root of M over K. K didn't change, M didn't change, 2 and pi didn't change. So it's going to be the same. This is just like your pendulum stuff. Remember, the amplitude does not care about the period. Find the expression of R in terms of those guys. Okay. Nice, nice. So what do we got to do here? We got to figure out the speed of block 2. Okay, so remember, block 2 has 1/4 of the kinetic energy, but once again, 1/4 of the kinetic energy is going to be the same thing as 1/4 of the spring energy. So that's what we're going to use to figure that out, and then we got to use that to do some kinematics here. So let's first figure out the spring energy. Oh, I need a different color. We'll go with light blue here. So first the energy. So your spring energy is going to equal your kinetic energy. So your K is going to equal your spring energy. So you're going to have 1/2 mv squared is going to equal 1/4 of this, right? So over 4. So that was 1/2 kx, and the displacement was 1/4 L squared. Nice. So solving for V. Cancel out those 1/2s. Cha-cha-cha. So V is going to equal big square root. We're going to have K. We're going to throw the 1/4 squared is 16 downstairs. It's going to make it a 64 again. And you do what you got to do. There's going to be an M downstairs from there, and you're going to have an L squared up top. Okay, let's just leave it like that. I don't know. Think it'll be all right? Hopefully. So now we got to figure out how far it will go. So it's going to start off with a vertical velocity of 0. We have to figure out the time. All right. So I'm going to grab a different color just for now. So falling straight down, we're going to have a distance of h. This is using the second big equation. 0 plus no starting velocity, plus 1/2 gt squared, solving for t. Time is going to equal 2h over g square root. Oh, g. There it is. Okay. So that's the time it takes to fall down, right? So now we have a time, we have a velocity. We just got to multiply them together because, we'll go back to blue here, r is going to equal the velocity times the time. The velocity is square root of kl squared over 64m times the square root of 2h over g. And you could wedge it all together in one massive square root if you were so inclined of kl squared 2h divided by 64 mg. And then, yeah, 1 over 32, but oh well. Okay, let's look at the nextest one. A bullet of mass m is fired from a non-lethal pellet gun horizontally with speed v into a block of mass m initially at rest. At the end of an ideal spring on a frictionless table, at the moment the bullet hits, the spring is at natural length. The bullet becomes embedded in the block and a simple harmonic oscillation result. Nice. So it's going to push the block in. And the speed of the block immediately after the impact of the bullet. Easy. So for this, we're going to do momentum. We have momentum of the bullet, which is mv. That's going to equal momentum of them together, which is going to be m plus big M times the new v. And this is what we're solving for. We'll call it v together. I don't know, just to make it different. So the velocity together is going to equal mv divided by big M plus little m. Yeah, I know. How about those m's? And that's it. That's the whole thing. So for part next, determine the amplitude of the resulting oscillation. So we're going to use conservation of energy. Hopefully you're noticing some patterns here. So we have kinetic energy is equal to the spring energy that we're going to have. Kinetic energy is 1/2 mv squared is equal to 1/2 kx squared. Cross out the 1/2. So for mass, the mass of the whole enchilada is going to be m plus big M times v squared. V is this guy right there. So we're going to have mv divided by big M plus little m. That's squared, and that's going to equal k times x. We're solving for x. Okay, so we can do a little bit here, where we got an m squared, a v squared, and these guys squared, just like before, really. This can cancel out with one of those, just to make it a little bit less tedious. So what's left over here, we're going to have a little m squared, a v squared, divided by a big M plus a little m, and we're also going to divide by k. And we're going to square root the whole thing. And that's what x is going to equal. Nice. All right, for the final one, compute the frequency. Easy. We have a formula for period. It's 2 pi square root of m over k. All right, so our period is going to equal 2 pi square root m is going to be m plus big M over k. But it wants frequency, but frequency is equal to 1 over the period. So all you're going to do is reciprocal this whole enchilada here. So your frequency is going to equal 1 over 2 pi square root of m plus big M over k. Now you could just reciprocal 2 pi and then flip-flop the fraction and under the square root. Yeah, there's a formula for that too, but why bother? All right, so you're going to do the last one. I think the last one's the first one, but that'll make sense in a second here. See ya. All right, never mind about all that. Let's do it. Okay, so a block of mass big M oscillating with an amplitude of A on a frictionless table is connected to an idealized spring with a force constant K. The period of oscillation is T. At the moment when the block is at position half. It is moving to the right. Block of clay mass, little m, is dropped on above and lands on the block. Nice, so beautiful. All right, so we'll start at the tippity top over here. What's the velocity of the block just before the clay hits? Well, we're going to have conservation of energy. At this position right here, we have kinetic energy, and we also have spring energy. Now that's going to add up to the overall spring energy, which we are most familiar with. So kinetic energy is going to be 1/2 mv squared. And we're going to be solving for that v. That's what we're going to be looking for. And this is going to be added to 1/2 kx squared. So 1/2 k. But for x, x is going to be the displacement. What's the displacement here? It's 1/2 of a. Okay. And then moving on to the right-hand side, we've got 1/2 kx squared. What's our displacement for this situation? It's going to be all the way, so at a, right? That's the only other situation we know enough about. So that's that. So now we're solving for v. So let's take out all these 1/2s, just like you should be used to by now, really. So mv squared is going to equal, we're going to have ka squared minus, well, when you distribute the squared here, we're going to have 1/4 ka squared. Nice. So 1 ka squared minus 1/4 ka squared. So our v is going to equal 3/4 ka squared. And we're going to divide by m. So let's throw the m down there, and we're going to square root. And that's it. So this is the before velocity. I'm going to write that just because we're going to have to figure out another velocity in a second. So I want to keep them straight. All right, what's the velocity of the block just after the clay hits? Well, we're going to do momentum here. So momentum, we're going to have m times v of the block is equal to m times v of them together. So we're going to be solving for this v right there. So m for the before is going to equal just big M, right? The block has no momentum. P is equal to 0 because it's going straight down. We only care about left and right momentum right now. Well, what's the velocity of the block? Well, we just figured that out. That's the before velocity. So that's going to equal a big square root of 3ka squared over 4m. All right. Let's see. That should be a big M, because that's the mass of the big block. But we just want to make sure we don't get it all tangled in there. All right, and then that's going to equal M. Well, what's the mass of them together? Well, it's going to be M plus big M. V is going to be V because we're solving for that. All right, ready for it? Let's solve. So V is going to equal, let's do big M divided by little m plus big M. Right, and then just the big square root sign after that. So 3ka squared over 4 big M. Nice. So wonderful. There's some simplifying you could do, but who cares, right? So this is the after velocity. Now we're looking at the next one. What is the new period of the oscillation of the block? All right. So this one's easy because you have a formula for it. T is equal to 2 pi square root of m over k. Well, the new period is going to be T is equal to 2 pi and then square root. What's the mass? The mass is little m plus big M over k, and that's it. Doesn't have anything to do with the previous stuff right now. What is the new amplitude? Oh, new color. New color. The Christmas connection. What is the new amplitude of the oscillations? Write your answer in terms of stuff. Okay. So the new amplitude. So that's going to be where the kinetic energy is 0 and the spring energy is everything. So since we only know about this position right there, so we have to work from that position. So we're going to have the kinetic energy of that halfway mark plus the spring energy of that halfway mark. We want to see when it equals the maximum spring energy. This is very similar to the purple problem here, except we're doing it post-collision instead of pre-collision now. So we know the kinetic energy. It's going to be 1/2 times mv squared. M is going to be little m plus big M. We know the V. The V is going to be this whole enchilada there. So we're going to have a big M over a little m plus a big M times a big square root of 3k a squared over 4m. And that's all squared. Okay, so plus 1/2 kx squared. Well, what's the displacement? The displacement is 1/2 of a equals the spring energy. What's the spring energy going to be? Well, it's going to be 1/2 kx squared. And we're solving for that x. We want to know what the amplitude is. What's the maximum displacement? All right, so before we just jump into solving for x, let's see what we can cancel out here. Everything has a 1/2. We can take out that. All right, if we distribute this squared here, we are going to get an m squared over that sum squared, and then this square root goes away. All right, reason why we're doing this is because the bottom is squared in this one, so this guy is taken out, and it takes out the squared. This m takes out the squared of that m. All right, so all of this is gone. Anything else? Well, right now the k is out of the square root, and we have a k for everything, so we can cross out those k's as well. All right, now you don't have to do this all at once like I do, but I had a practice round, which you didn't see, I guess, and I don't have a lot of room. So now when I write everything that's left over here, so I'm going to have big M over little m plus big M times, I've got a 3a squared over 4 right there, plus a squared over 4, because, distribute that squared. And that's going to equal x squared, so I'm going to square root this thing. So that is equal to x. So that is the maximum displacement, or maximum amplitude. So would the answer to part C be different if the clay had been dropped at a different position? Let's see, C was oscillation. No, because it does not depend on mass. Or sorry, does not depend on location, only mass. Right, because that's the formula right there. There's nothing to do with anything but mass and K. Didn't change K. Would your answer to part D be different if the clay had landed on a different part? Yes. So part D is talking about the amplitude, the one we just went through. The reason why the amplitude would change is because of these kinetic energy depends on the location, and the spring energy depends on the location. Maybe that doesn't help you out too much here. Let me give you an example. All right, whatever. Okay, one example that's easiest. If you have, let's go the other way. Let's try to match the picture. Here's your spring. If you had it stretched all the way out and then you dropped it on there, it would not change the amplitude because the amplitude is already at its maximum. So that's why it does this. And that's why the location will depend on that. That's why they were very specific in how they described it. Okay, hopefully that helps you out. Easy physics all the time. Like and subscribe to see the next videos.